Hello everyone. Welcome. Welcome to this ARSET training on Earth observations for disaster risk assessment and resilience. My name is Amita Mehta and I will be conducting this webinar with the help of my colleague Sean McCartney. To begin with, these are the learning objectives of this training. We'll start with learning about available NASA remote sensing and socioeconomic data and how to combine them for disaster risk assessment or DRA. We will be using DRA for disaster risk assessment throughout this webinar. Next, we want to understand how to apply these data for assessing risk for floods, tropical cyclones, and extreme heat in specific regions. So these are the disasters we're going to focus on to begin with. Next, we are going to demonstrate how operational agencies are using NASA data for risk management. So these are the overall objectives. There will be 4 parts to this training. 2 sessions will be this week and 2 next week. Each of these will be repeated twice, one from 10 to 12 and then 3 to 5 Eastern US time. Today we will start with NASA remote sensing and socioeconomic data for disaster risk assessment. Then later this week, we will have demonstration of how these remote sensing data can be used to assess risk for floods and cyclones. Next week, we will have guest speakers talking about disaster risk assessment case studies using remote sensing data. And finally, we will have operational application of remote sensing data for disaster management. There will be 2 homework assignments. One will be given at the end of this week and the next one at the end of the webinar series. There will be also a certificate of completion awarded to attendees who attend all 4 sessions and complete both homework assignments by 30th of August. Also, please note that the homework assignment must be submitted via Google Forms, and the links to the forms will be provided when the homeworks are posted. After the webinar series is over, you will receive certificate of completion in approximately 2 months after the series is over. So we'll start with today's session. Our outline is here. We will talk about ARSET briefly. Then we will talk about DRA concept and definitions. We will have overview of remote sensing and Earth system model data sources relevant for DRA. And then we will have a guest speaker talking about socioeconomic data relevant for DRA. To start with, we'll have an introduction to ARSET. ARSET is set up to empower global community through remote sensing trainings, and it seeks to increase the use of earth science in decision making through training for policymakers, environmental managers, and other professionals in these themes: air quality, disasters, land and water, as shown here. These are the themes, and we have a team. We have instructors located at several NASA centers as listed here, and we have a support group that helps us plan the training. ARSET trainings are online, such as this one, and there are also in-person trainings. Most of them are given in 2 languages, English and Spanish. Online webinars have multiple sessions and they last from 1 to 5 weeks. In-person trainings, depending on the theme, last from 2 to 7 days, and it's typically held in a computer lab, and it focuses on locally relevant case studies. There are fundamentals of remote sensing trainings available online. Also, there are introductory and advanced level trainings given by ARSET, depending on different themes and how the requirement is defined by end users. This is the statistics of how ARSET has done in last 10 years. This is our completing 10 years of trainings. And as you can see, these are the themes, these are the years, and over the years, we have reached out to about 19,000 plus participants from 160 plus countries with many organizations. And overall, 110 plus trainings have been given in these years. This is ARSET listserv link. If you are not a member of ARSET listserv, we recommend that you join it. That way you can stay up to date with ARSET activities, and you can also receive and look at newsletters and learn about upcoming trainings or any tools or any data that have come up. With that, we will start disaster risk assessment, concept and definitions. We're going to follow definitions given by UNISDR, or which is now UNDRR, Disaster Risk Reduction Agency. So we're going to use these terminology based on UN definitions. Disaster risk assessment is a process to determine the nature and extent of risks, which requires analysis of hazards and existing conditions of exposure and vulnerability, and it focuses on potential harm to people, property, services, livelihood, and environment in which people live and ecosystems depend on. So a comprehensive DRA actually evaluates the magnitude and likelihood of potential losses. It provides full understanding of the causes and impact of those losses. DRA is really an integral part of disaster risk management, which is decision and policy making processes and requires close collaboration among various parts of the society. So we are going to go through each and every term that we have listed here, which are part of overall disaster risk management, and most of these are part of disaster risk assessment. To start with hazard, it's a process, phenomenon, or human activity that may cause loss of life, injury or other health impacts, property damage, socioeconomic disruption, and environmental degradation. A hazard is characterized by location or geographic area, intensity or magnitude, frequency or return period or probability of occurrence. This depends on the type of hazard, and as listed here, hazards can be either natural or they can be human-induced. So natural hazards are listed here. In nature, they can be geological, such as earthquakes, landslides, and volcanoes, meteorological, which are storms, extreme temperatures, wildfires, extreme precipitation. You can have hydrological, which also includes floods and drought and extreme precipitation. Oceanic, where you have ocean wave surge. Biological, it's diseases and epidemics. Human-induced hazards include industrial and transportation accidents, environmental pollution, human conflicts, human migration. These are all cause of hazards. Now, in this webinar series, we will be focusing on natural hazard only. So what is exposure? As we said, that DRA depends not only on hazard type, but also on exposure and vulnerability. So exposure is the situation of people, infrastructure, housing, production capacities, and other tangible human assets located in hazard-prone areas. So exposure can be measured by the number of people or types of assets in any area. And to estimate quantitative risk associated with a hazard, exposure measurements can be combined with specific vulnerability and capacity of exposed elements. So what is vulnerability? Vulnerability is actually determined by physical, social, economic, and environmental factors or processes, which assesses the susceptibility of an individual or a community, asset, or system to the impact of hazards. How vulnerable a particular sector of society is or infrastructure is to hazard is what a vulnerability is representing. So it depends on cultural and institutional factors as shown here: poor design and construction of buildings, poor environmental management, inadequate protection of assets, lack of public information and awareness, levels of poverty and levels of education, limited official recognition of risks and preparedness, and weak governance. So it depends on are there any mitigation steps placed for disaster or not, and so vulnerability depends on all these factors. So that brings us to again talking about disaster. So we talked about hazard, and now we're talking about disaster. So a hazard is, as we talked about, could be of natural origin or human induced origin. But here, disaster is a serious disruption of the functioning of a community or a society at any scale due to hazardous events leading to one or more of the following losses and impacts. So human lives are lost, material is damaged, economic losses, and environmental degradation or losses. So disaster is really the end result of hazard. Now, if hazard occurs where there is no exposed population or vulnerable population or communities, then it's not really a disaster, it is just a natural hazard. When it's combined with how it is affecting these factors, then it becomes a disaster. Disaster risk is the potential loss of life, injury, or destroyed or damaged assets that could occur to a community as a function of a hazard, exposure, or vulnerability. And so here it is shown that this made up of these parts all have to come together, and that's the disaster risk. What kind of hazard it is, how much exposure there is, and what's the level of vulnerability, and that decides disaster risk. And what is disaster resilience? We have heard about disaster the resilience to any hazard, and that is ability of a system, community, or society exposed to hazards. So it can resist, absorb, accommodate, adapt to, or recover from effects. That is resilience to any disaster. And it refers to the timely and efficient response, including through preservation and restoration of basic structure and functions. So how resilient to any disaster a community or society is, that is really the resilience. So disaster risk reduction, it is aimed at preventing new disasters, reducing existing disaster risk, managing residual risk, and these contribute to strengthening resilience. So DRR is required for resilience. It involves developing strategies and policies across different timescales with concrete targets, indicators, and timeframes. So that is disaster risk reduction, which really depends on understanding each and every factor and then designing strategies and policies so that there is reduced risk to any disaster. Finally, disaster risk management. It is the application of disaster risk reduction. So it's the policies and strategies, they are in place to prevent new disasters, reduce existing disaster risk, manage residual risk, and they can be categorized as shown here. It could be prospective DRM, it could be corrective DRM, or it could be compensatory DRM. And so these are some of the terminologies that is provided by UN, but basically it is the strategies and policies as a result of understanding all these factors for a given location, and then disaster risk reduction policies lead to disaster risk management. So this is how to conduct a disaster risk assessment is shown here. This is based on UNDP or UN Development Program. It's a busy slide, but what it basically shows is that you need to understand systemic inventory and evaluation of existing risk assessment studies, available data and information, and current institutional framework and capabilities. So these are required for DRA. So it starts with hazard assessment. That means identify prevailing hazard, the location, intensity, likelihood. It could be either single or multiple hazards such as storm and flood or landslide and earthquake. And then leads to exposure assessment, which is identifying population assets at risk and delineate disaster-prone areas. Also, vulnerability analysis, which requires determination of the capacity of a system to withstand given hazard scenarios. And loss and impact analysis, which requires estimation of potential losses of exposed population, property, services, livelihoods, and environment. and it assesses their potential impacts. These leads to risk profiling and evaluation, which is identification of cost-effective risk reduction options in terms of socioeconomic concerns and capacity. And that leads to formulation or revision of DRR strategies and action plans, and that leads to a proper disaster risk management. So the steps shown in this red boxes here, they can be accomplished by using open source NASA data, and that is the focus of our next section. So here are some of the natural hazards: cyclones, droughts, earthquakes, extreme precipitation and temperature, floods, landslides, tsunamis, volcanoes, and wildfires. If you look at this UN statistical chart from 1998 to 2017, it shows that in this time frame, this is the floods. Number of disasters occurred, so floods is 43.4%, followed by storms, which is 28.2%, and then earthquake, extreme temperature, landslide, drought, wildfire, volcanic activities, and mass movement. So as you can see, floods and storms, they dominated number of disasters during this time frame. If you look at the number of people affected by these disasters in the same time frame, you can see that again floods, droughts, and storms, they affect most people in billions here, and so you can see that majority of people are affected by these disasters, and then of course there are other disasters affecting population as well. In number of deaths occurring because of these disasters between 1908 and 2017, earthquakes seems to be the disaster where a lot of deaths occur, partially because it suddenly occurs and there is maybe no time to respond, and that's why there are so many deaths. Next one though, as you can see, it is storms, and then extreme temperatures and floods. So again, it appears that storms, floods, temperatures, these weather phenomenon, they affect a lot of people. And so based on these statistics, what we're going to do for this webinar series, we're going to focus on these three disasters, or three hazards, I should say: cyclones, urban floods. We're going to talk about extreme precipitation and focus on urban flooding, and extreme heat. So these are the hazards that we will be focusing on. So assessing the potential risk of a hazard, that requires identification of nature, location, intensity, and likelihood of major hazards prevailing in a community or environment. And what that requires is data and information about the type of hazard or multiple hazards affecting the community or area. And that requires looking at past or historical data to identify hazard-prone regions, assess frequency and probability and intensity of hazards, and establish strategies for disaster risk reduction. Also, it requires current data for near real-time action for disaster risk reduction. So based on DRA, based on past data, you can apply from that experience how to deal with current disasters. Also, future data or forecast also help in assessing potential risk of an approaching hazard, and then planning for near future action or for disaster risk reduction. It is important to note that for this to be accomplished, not only we need proper data, but quantitative analysis of this past, current, and forecast data are required for assessing potential risk of any hazard. So there are data needs for the hazards that we want to talk about. So cyclones, one would like to know in any region what the frequency of cyclones is, probability for each season, and intensity. And for that, one requires past data of cyclone tracks, landfall locations, storm surge, sea level pressure, winds, precipitation. For flood, it is floodplain extent, frequency, intensity, and duration. These are helpful in designing disaster risk reduction strategies. And for that, one requires precipitation data, soil moisture, terrain and slope of the location, and impermeable surface, or surface where water cannot percolate into the ground, but it stays waterlogged. So these are the data sets. They can help in understanding hazard assessment for floods. Extreme heat, also for that, frequency, probability, and duration, they are required to assess type of hazard, extreme heat. And then that requires data such as surface temperature and surface humidity. Some of these data, or most of these data, are available from NASA Earth observations and models. So the data listed in blue are available from NASA, and the one in brown, they are available from other centers, from NOAA, from Joint Typhoon Warning Center. Also, there are worldwide tropical cyclone centers. So these, they provide information on these hazards. So that brings us to remote sensing data sources which are relevant for disaster risk assessment. We will review NASA remote sensing and Earth system model data, which are available for long-term as well as in near real-time and for forecast, so that past data can be used for understanding intensity, frequency, and spatial extent of hazards that have already occurred. And then together with real-time data and forecast data, that information can help in better preparedness in response to that hazard. So we'll start with long-term data sets. They're available for more than 18 years, and we're going to focus on 3 hazards, as I mentioned earlier: extreme heat, cyclones, and flooding resulting from extreme precipitation systems or cyclones also. These are the parameters listed here. Sources of this data are listed here, and spatial and temporal information is provided in these 2 columns. Please note that all the acronyms given here are defined at the end of this presentation slides, and you can review them. We will briefly go over the table. For extreme heat, land surface temperature, surface air temperature, surface humidity are relevant. They can help in understanding in which area most intense extreme heating is occurring. And so for past data, looking at this past data, one can come up with frequency, spatial extent, and probability of extreme heat hazard in different locations. Sources of these parameters are MODIS, which is a sensor flying on Terra and Aqua satellites; Global Land Data Assimilation System model. This is a reanalysis model. Both these models use satellite data assimilated in them, or in GLDAS, they're used as forcing, and these provide temperature and humidity information. Winds are also available from MERA2. They are useful for understanding where very high speed wind occurring because of cyclones. Precipitation, which is very relevant for flooding and cyclones hazard, they are available from 2 satellites, TRIM and GPM. Both these satellites have this multi-satellite precipitation product, TMPA and iMerge. They are available for a long time. Here it is important to note that TRIM, which was launched in 1998, stopped functioning in 2015, but the data were continued with climatological calibration, and they're still available in present. And GPM was launched in 2014 February, and so those data are available, but now recently combined TRIM GPM product is available, also known as iMerge, and that is spanning 2000 to present at 1/10 of a degree resolution, half-hourly spatial resolution. So that data can be used for flood and cyclone hazard assessment. Soil moisture, which is relevant for flood assessment, is available from GLDAS and MERA2. We're talking about long-term data sets here. And elevation, which is relevant for flooding, looking at topography and slope and low-lying area. It's available from this shuttle radar topography mission. So this is really not available for more than 18 years, but it's actually was measured in 2000, and so that static data is used for topography all these years. So that's why it's listed here. As you can see, resolutions in space, they vary for different data sets. SRTM is about 30 meters, ranging MODIS is 1 kilometer, quarter degree for TRIM and GLDAS, half a degree for MERA and 1/10 degree for GPM. So resolutions do vary, but these data are available for long term, and they can be used to assess these hazards regionally where there is intensity is high or frequency is high. What is the probability or return period? Also, there are data sets available for last 4 to 5 years from these sources. So precipitation, again, as we mentioned, from GPM alone, they are available from 2014 March, but the long-term data set is also available in from 4 to 5 years, all the way from 2000, so that can be used too. Storm surge, that is available from a NOAA model. It's called SLOSH, which is useful for cyclone, with resolution of tens of meters to a kilometer. That's available since 2014. Soil moisture is available in past 4 to 5 years from these two sources. GEOS 5 is a Goddard Earth Observing System model version 5, and SMAP is a satellite soil moisture active passive that was launched in 2015, and the data are available from April of 2015. So here also you can see that resolution varies from here it is 9 kilometer, 36 kilometer all the way to 1/10 of a degree, 0.3 by 0.25 degrees. So, but they have good temporal coverage, and other than SLOSH, all these data are global in extent. This brings us to near real-time and forecast data. So once you know hazard assessment from past data, that information can be applied to hazard that is occurring in real time or one that is approaching, which you know from forecast, and then that helps you in better preparedness. So the same data sets are listed here for these hazards, and so MODIS, it's available in real time. GEOS 5 provides data in real time as well as 10-day forecasts are available. SMAP provides near real-time data. GPM iMerge also provides near real-time data, and SLOSH, of course, has real-time data in addition to there is 48-hour forecast also available. So these are the overall data sets that can be used for hazard assessment. This is a list of ARSET webinars that were conducted in last 2 years. All the data sets that we talked about, the past data as well as near past, near real-time and forecast data, they're described in these webinars in great detail. Also the satellites and sensors we talked about, such as MODIS from Aqua and Terra, TRIM GPM, SMAP, even SRTM, which is the Shuttle Radar Topography mission. Models such as GLDAS and MERA and GEOS 5, they are all described in this webinar. These two webinars, Remote Sensing for Disaster Scenarios and Monitoring Tropical Storms for Emergency Preparedness, they provide information and details of the datasets themselves and how they are applied for these different applications. So we recommend that you go through or review these webinars for detailed information about satellites, sensors, models, and datasets. This is a list of data access tools. Next session, we will have demonstration of some of these tools, but this is just a concise information about the data tools. There is Giovanni and NASA Earth Data GS disk that can be used to obtain MERA2, GLDAS, TRIM, and GPM data. There is Precipitation Measurement Mission that also provides TRIM and GPM data access. A tool called Appears that can be used to get SMAP and MODIS data and GEOS 5 forecast data. Near real-time and forecast data, they can be obtained from this NCCS data portal. Finally, the SLOSH model that we talked about that provides storm surge, that is available from this probabilistic tropical storm search or P-search tool. And so here are all the links. And again, we will review some of these tools and demonstrate some next week. So hazard assessment for disaster risk reduction. So these are the steps required. On this side, there is a chart provided by World Meteorological Organization that talks about examples of disaster risk reduction applications and lead time for information required. So here, as you can see, say for early warning and emergency response operations, you need alerts, watches, and warnings. It requires information on this time scales from minutes to hours to days. Similarly, if you need sectoral preparedness planning, inventory management, insurance contracts, etc., that also requires not only alerts, watching, but also forecasts. And here is the time scale that is required. For longer time lead, they're required for strategic planning, for mitigation planning, and governments can put strategies and policies in place. So these are long-term requirement. What we are going to focus on in next 3 weeks is basically in this time frame from hours to days to weeks to maybe a month or a season. So here, as listed, analysis of past data that helps identify hazard-prone areas, intensity and frequency of hazards. Based on these past hazard analysis, together with exposure and vulnerability data and socioeconomic impact, which is basically disaster risk assessment, that can help prepare for current and future disaster risk reduction. And that eventually leads to planning for overall disaster risk management. So what we talked about right now is the past data and near real-time and forecast data for hazard assessment. Next, we have to know about exposure and vulnerability to have proper disaster risk assessment. So together with hazard assessment, what is needed is exposure, which is elements at risk, and vulnerability, which can be physical, social, economical, or environmental type. And so these data are also available from Socioeconomic Data Center. And so next, we are going to have a guest speaker from CDAC, Dr. Susanna Adamo. She will present socioeconomic data relevant for exposure and vulnerability for disaster risk assessment. Before I hand it over to Dr. Adamo, here is a reference, all the acronyms that we came across for different data sets, satellites, sensors, models, they're listed here. With that, I invite Dr. Susanna Adamo from Columbia University. She will talk about socioeconomic data relevant for disaster risk assessment. Susanna?
The Socioeconomic Data and Application Centers, or CDAC, is one of the Distributed Active Archive Centers, or DACs, in the Earth Observing System Data and Information System, EODs, of the U.S. National Aeronautics and Space Administration, NASA, and is hosted by CSIN at Columbia University. In a nutshell, CDAC data provide the human context for NASA remote sensing data. CDAC role within the NASA DAC is to function as the information gateway between the physical sciences and the social sciences to support greater public understanding of the impacts of climate change, as well as the generation of policy relevant information to inform strategies for mitigation and adaptation. In addition, CDAC aims to facilitate the analysis and portrayal of the human dimension of global change and to provide for the archive of and access to relevant socioeconomic data sets. All of CDAC data is open and freely available through its website after registration. In terms of priorities, SPACEX priorities include human settlement, infrastructure, and population data, drawing on a range of remote sensing and other data sources, policy-relevant sustainable development indicators, especially in areas where selected NASA remote sensing datasets are available, operational use of SPACEX data and services through a range of user interfaces, value of integrating remote sensing and socioeconomic data in both research and applications. In terms of communities, SPACEX offers direct support to scientists, applied and operational users, decision makers, and policy communities, and also has strong links to the geospatial data community. And for all this, it puts a big emphasis on data integration, tools, and services. Now, before describing a subset of SPACEX datasets relevant for exposure and vulnerability information, it is useful to define these terms. Following the fifth assessment report of the IPCC, exposure refers to the presence of people, livelihoods, species or ecosystems, environmental functions, services and resources, infrastructure or economic, social or cultural assets in places and settings that could be adversely affected. While vulnerability is the propensity or predisposition to be adversely affected, vulnerability encompasses a variety of concepts and elements, including sensitivity or susceptibility to harm and lack of capacity to cope and adapt. In today's session, we will describe some of SPACEX datasets useful for exposure and vulnerability information. For exposure, we will look into the population distribution with the gridded population of the world, GPW4, version 4, and with infrastructure location using global reservoirs and dams, GRAND, global roads and open access dataset, SHE-ROADS, and population exposure estimates in proximity to nuclear power plants. For vulnerability, we will explore basic demographic characteristics dataset that is part of the GPW4 collection, looking at children, older adults, and gender, and the global subnational infant mortality rates dataset. The gridded population of the world, or GPW4, currently in its version 4, models the distribution of human population in terms of count and density on a continuous global raster surface. Its purpose is to provide a spatially disaggregated population layer that is compatible with datasets from social, economic, and earth science disciplines and remote sensing information. The outcome is a globally consistent and spatially explicit data for use in research, policymaking, and communications. As illustration, the map on the right displays the population count for 2010 in a global 1-kilometer grid. The essential input for GPW4 are population census tables and corresponding geographic boundaries. There are several steps to develop GPW4. The first steps are to find tabular population counts for the 2010 census round for all the countries in the world. Then match the tabular counts to geographic boundaries, either census or administrative boundaries, and adjust the boundaries to a global framework and mask inland water. We then estimate the population for the target years from 2000 to 2020 in 5-year intervals, and adjust then to the UN World Population Prospect for the target year. Finally, we proportionally allocate population to 1 kilometer grids using an areal weighting method. The proportional allocation or areal weighting method uniformly distributes population based only on land area. This maintains the fidelity to the input data. But on the other hand, the accuracy of a GPW pixel estimate is directly related to the size of the input census units, which varies widely among countries. For example, the average input unit resolution for very high developing regions is about 900 square kilometers. The average input unit resolution for very low human development countries is around 3,500 square kilometers. Accuracy would be higher for the former than for the latter. Turning now to infrastructure, the dams dataset is part of the Global Reservoir and Dam Dataset Grant, which is an outcome of the Global Water System Project. Its purpose is to provide a single, geographically explicit and reliable global database describing reservoirs and dams characteristics and geographical distribution. It includes about 6,800 records of reservoirs and their associated dams with a cumulative storage capacity of around 6,000 cubic kilometers. The outcome is a high-resolution mapping of the world's reservoirs and dams for sustainable river flow management. And the map on the right displays one of these layers. In terms of methodology, the dams were geospatially referenced and assigned to polygons depicting reservoir outlines at high spatial resolution. Dams have multiple attributes, such as primary use, nearest city, area, name of impounded river, year of construction of commissioning. As an example, the map on the right displays the location of the dams where the colors indicate their main use, fisheries, flood control, irrigation, etc. Another infrastructure-related dataset is the Global Roads Open Access Dataset, or G-Roads. It is an outcome of the CODATA Global Roads Data Development Task Group, led by CECIM. Its purpose is to provide an open-access, well-documented global dataset of roads between settlements using a consistent data model, which is, to the extent possible, topologically integrated. The final product is presented in the map to the right of the slide. CDAC is working on a new service to disseminate regularly updated OpenStreetMap roads data in GIS-ready file format. The complete methodology for developing the dataset is available in the documentation. But in brief, G-Roads combines the best available public domain roads data by country into a global roads coverage using the UN Spatial Data Infrastructure Transport version 2 as a common data model. The country road networks have been joined topologically at the border, and many countries have been edited for internal topology. The source data as a percentage of the total road network for each country are also provided in the documentation. An example is the map on the right that compares the availability of the map versus other sources by country. Because the data are compiled from multiple sources, the dates for road network representation ranges from the 1980s to 2010, depending on the country, and most countries have not confirmed dates. And also, spatial accuracy varies. Finally, the population exposure estimate in proximity to nuclear plants combines information from a global dataset developed by Declan Butler of Nature News and the Power Reactor Information System, PRIS, an up-to-date database of nuclear reactors maintained by the International Atomic Energy Agency. The purpose is to provide a global dataset of point location and attributes describing nuclear power plants and reactors. The map on the right shows the nuclear power plant location layer of the dataset. Now, in terms of methods, the location of nuclear reactors around the world are represented as point features associated with reactor specification and performance history attributes as of March 2012. The country-level aggregate dataset consists of country-level estimates of total urban and rural population and land area that are in proximity to a nuclear power plant. The power plant locations are represented as point features associated with population exposure estimates for the years 1990, 2000, and 2010 within 6 buffer zones. As an example of nuclear plants points and attributes, the table on the right displays the information for the Koeberg nuclear plant in South Africa, the red dot in the map. Turning now to vulnerability, we talk about the basic demographic characteristic data set, and GPW version 4 includes this data for the first time as age at 5-year age groups and sex surfaces at the subnational level. The purpose is to provide estimates of population counts by age and sex for the year 2010 as raster data to facilitate data integration. The data is presented as global rasters at 30 arc-second horizontal resolution, approximately 1 kilometer at the equator, one raster for each age group and sex. Two outcomes of this dataset are the maps on the right, which display the distribution of the proportion of children under 5 in the upper panel and the proportion of the elderly in the lower panel as indicators of young and aging population respectively. The methods for developing the basic demographic characteristics dataset are similar to the methodology for GPW4. First, we estimated male and female populations and male and female population by age for 2010. Then we decided on what would be the last age group. For countries with available data, 5 upper age group classes were calculated from the age estimate, starting at 65, going up to 85 and plus. Because of data availability, the highest global coverage is for 65 and older. After that, male and female age groups were summed to produce the estimated total population in each age group for 2010. Population data were matched to geographic boundaries, census or administrative, and boundaries adjusted to a global framework. Finally, population data were allocated proportionally by age and sex to 1 kilometer grid using an areal weighting method. Other vulnerability-related dataset is the Global Subnational Infant Mortality Rate version 2 for 2015. It was created to provide a global subnational surface of infant mortality rate estimated for the year 2015 to be used by a wider user community in interdisciplinary studies of health, poverty, and the environment. The 2015 dataset includes infant mortality rate, or IMR, estimate for 234 countries and territories, 143 of which include subnational units. The map on the upper left side indicates what administrative level was used to report the IMR, and in some countries, more than one level was used, for example, in Brazil, to take advantage of the availability of data at higher resolution for some districts. The graph in the lower left side shows the distribution of the IMR input values and helps to spot outliers that could indicate suspicious cases, very low or very high rates. So how was the database built? First, IMRs were collected from vital registration records, surveys, models, and other estimates. Alternately, IMRs were estimated using reported data on live birth. This is the denominator for calculating the rate, and infant death. This is the numerator for the target year. Input data was then adjusted to account for multiple input sources spanning from 2006 to 2014. The final data is then consistent with the national estimate for the year 2015 of the latest version of the United Nations Interagency Group for Child Mortality Estimation Report. The map on the right shows the final outcome, and it indicates that infant mortality continues to be higher in sub-Saharan Africa and Southeast Asia. We will now show how these datasets are applicable to the case of Cyclone Idai. First, we look at the characteristics of the event. Idai made landfall in Mozambique, close to the city of Beira, as an intense tropical cyclone on 14th of March. It landed as a Category 4 out of 5 on the scale used in Mozambique. Winds reached 165 or 155 kilometers or 102 miles per hour, with gusts of up to 230 kilometers or 143 miles per hour. In addition to the hurricane winds, there were torrential rains and very high seas, with waves height reaching 10 meters or 33 feet. There was catastrophic deadly inland flooding due to the heavy rains that lasted from 13th to 21st of March, particularly in the Busi and Pungwe rivers. And the rainfall accumulation is displayed in the map to the right of the slide. In terms of the impact of the event, there has been more than 600 deaths, about 1,600 injured, more than 1 million people affected, and an estimated $773 million in damages to buildings, infrastructure, and agriculture, and these represent about 5% of Mozambique's GDP in 2018. How SIDAC data is applicable to Cyclone Idai? One application is to map or locate population and infrastructure to explore and evaluate exposure using GPW4, GRAND, and G roads. On the left is the distribution of population counts for Mozambique in 2015, showing that the Idai's landfall area is between densely and moderately populated area for Mozambique. The center map shows the distribution of dams, with at least 2 dams in Mozambique in the path of the storm. Finally, the map to the right is from G-roads and displayed the road density in Mozambique, including the affected area. For exploring vulnerability, we can use age composition from the basic demographic characteristics and infant mortality as a proxy for living conditions. The maps on the left at the center display the distribution of children and the elderly, respectively. The difference in distribution between the two maps responds to the fact that Mozambique has a young population with more than 35% of children, broadly distributed, while the older population is smaller and more heavily concentrated in urban areas. Finally, the IMR map on the right indicates that the area affected by EDE displays relatively higher infant mortality rates than other areas of Mozambique. These are the links to the databases described so far. Breeder Population of the World version 4.11, Basic Demographic Characteristics version 4.11, Global Subnational Infant Mortality Rates version 2, 2015, Global Reservoir and Dam Grant version 1, Global Roads Open Access Dataset SHE-ROADS version 1, and Population Exposure Estimates in Proximity to Nuclear Plants version 1. We turn now to a set of CDAC tools useful for visualizing exposure and vulnerability information. They include CDAC Population Estimator Service, a web-based service for estimating population totals, basic demographic characteristics, and related statistics within a user-defined vision. CDAC Hazard Mapper and CDAC Hazard and Population Mapper app. It enables users to visualize data and map layers related to socioeconomic, infrastructure, natural disaster, and environment data, and analyze potential impacts and exposure. The PopGrid Data Collaborative, which is a consortium of data producers, data users, donors, and other stakeholders, it offers a map viewer for comparing population grids from different data providers. The CDAC Population Estimator is useful to have a first glimpse to the magnitude of exposure and degrees of vulnerability. The screenshot is centered in Mozambique, and the layers displayed are shown in the legend, boundaries, and population counts. Using the polygon tool on the left, we can draw or define the area of interest, in this case, an area affected by EDE and including the city of Beira. When the selection of the area is completed, a pop-up window displays the population estimates and projection for that area, including broad age groups for 2010, and in this case, we are looking at the population trend between 2000 and 2010. And if we click in the 2010 age pyramid tab, we get the distribution of the selected area population by age and sex. Both in the trend and in the age pyramid tabs, the menu on the upper right corner of the pop-up window provides options for downloading and printing the underlying tables and the graph. The PopGrid map viewer allows comparing population estimates. This is a screenshot of one of the views of the PopGrid comparison tool. We have here 4 population grids from different data producers. The aim is to help users to decide what product better fits their needs. We have the Global Human Settlement Layer, or GSPOP, GPW4, World POP, and SRIS World Population Estimate. The screen shows the population in 1 pixel in or close to the city of Beira, the same pixel in each grid, and we got 4 different population estimates. Clicking in the expand icon on the upper right corner, and we are in the global view with GPW4 as the top layer. Once again, we center in Mozambique, and we select or define an area using the drop polygon tool on the left, and in a similar way as the population estimation service we just explored. The pop-up window now shows the population estimate for the user-defined polygon for the 6 global population grids included in PopGrid as a bar graph and as a table, although the table is not visible in this particular slide. Finally, we can use the hazard mapper to explore what is at risk in terms of populations, but also of infrastructure with several layers displayed at the same time. As mentioned, the same tool is available as an app, which is an advantage for using it in the field, for example. The screenshot is centers once again in Mozambique, and the red arrow shows the location of Beira. There is also an icon showing the location of the dam and green circles indicating settlements. This is the same screenshot, now with the legend up. Hovering the cursor on the dam icon in the map, and we can know the name of the structure, in this case, Bue Maria. Here are the links to the tools we just explored: the Population Estimation Service, CDAC Hazard Mapper and Hazard and Population app, PopGrid Viewer. And this is the list of the references cited in the presentation. Thank you.
Thank you so much, Susanna. We really want to thank you for your presentation and the excellent data sets that you presented, in addition to all the tools. On behalf of ARSET, we really want to thank you for your presentation. We have question answer session going on now. You can type your questions in the chat box or questions, and we will attempt to answer as many as we can. Also, at this point, I want to suggest that next Thursday, when we have our second session, we are going to continue talking about data sets that we saw today. We will demonstrate how to do hazard assessment. We're focusing on cyclones and flooding, and we will be using some of the data sets that we talked about today to do that. So we'll have demonstration of that. In addition, we will use some of the data sets that Susanna introduced today, and then try and see how these data sets can aid in disaster risk assessment. So we will look at specific case studies next session, which is on Thursday at the same time. Urban flooding is a difficult issue, as we will also address next week, not next week, but next session on Thursday. Either you use SAR or optical data. There are always limitations, even with SAR. In urban area, you can have double bounce or multiple reflection that can limit your flood detection in urban area. Optical data also, because of resolution, also presence of clouds, you may not be able to see urban flooding. So the urban flooding is a real issue, and we will see how we can go around using these data still, but using some additional data, what can we do to look at urban flooding? So for question 2, how these statistics are decided, and you can look at this PDF link provided here. And this is based on Center for Research on the Epidemiology of Disasters, or CRED. That's where all the information is coming from, and that is compiled by UN based on different governments, International Federation of the Red Cross, Red Crescent, World Bank, insurance companies, etc. And also based on press reports, or the disaster reports that come up from local news media. Question 3 is about what are the extent of these data. So the remote sensing and modeling data we talked about, most of them are global in extent, except for the SLOSH model, which is for storm surge, that is only for US, a coastal region. TRIM data we talked about, TMPA, that also has limited coverage in latitude. As it says, it's tropical, so it focuses between 50 south and 50 north. Other than that, all data are global. And Susanna, you may want to add this question 4. What is the meaning of fidelity?
Yes, fidelity to input data means that the data is not modeled. It means that whatever we get from the census data, that's the data that we use, and the only modeling that we provide is to assume that that population is uniformly distributed, where the administrative area for what that population was is the count. If you look at later in the presentation, we mentioned other population grids. Other providers use model data using ancillary data like roads or obstacles to allocate the population within the administrative area. That's not the case of CPW. The only is to do this areal weighting or proportional allocation. That's the only thing that we do. And that's why it's so important to know what is the resolution of the input data, because the larger the area, the more likely is that the weighting, the areal weighting is not going to be a very real representation. The good news is that the data is the census has more and more higher resolution. So that's the explanation.
Sean, you may want to answer question 5. Yeah, Sean, yeah, if you can.
Yeah, thank you so much. So the question is, who are the end users for disaster data products, and what kind of specific data products need to be developed or improved for them? The answer is, end users actually comprise quite a diverse group of people, from local, regional, and national governments to humanitarian organizations like the Doctors Without Borders, Médecins Sans Frontières, or the Red Cross, Red Crescent. There's also international institutions such as the World Bank. or United Nations bodies, as well as private companies. And private companies, I would use example, a lot of reinsurance companies use these spatial data sets to assess risk in areas for agriculture or other disasters that might impact economic productivity. So really the specific data product depends on the analysis needed by that private company or public entity. It could be used for, in some cases, long-term forecasting, maybe climate change related, near real-time forecasting. So it could be a hazard or an impending disaster such as a hurricane or a flood, or any specific application assessing historic risk and resilience to a specific disaster.
Question 6 is again about CDAC data. Susanna, I believe all CDAC data sets you presented are global, right?
Yes, they are global. All these data sets are global.
So they can be
yeah.
So question 7 is, how often does NASA update the data sets? So it varies with the data set. There is no specific timetable that every data set is updated every so many years or so. When a mission is launched, if it's a remote sensing based data, then during the lifetime of a mission, algorithms to derive data products are constantly being revised. After going through calibration and validation, newer version of data products, they come out. And so that depends on the development of algorithms throughout the mission lifetime. And so you will see, if you go look at data, you have multiple versions available sometimes. But usually as improvements occur in algorithm, then newer version come up. With models also, it's the same. If there is improvement going on in model parameterizations, then sometimes retrospective model runs are done. So it really depends on which data set you're talking about. So question 8 actually is very important. It keeps coming. We get this question: do you conduct a verification or validation of model data toward observations to apply on your research? How does one conduct it? So this, if you look at all the model data that NASA puts out or remote sensing based satellite data that come out, for all of them, there are validation programs in place, but they're not global. They are at selected places where there are detailed in situ observations available, and that is how these models and remote sensing data are validated. But we always recommend that in your own region and for your own application, we recommend you do your own validation. So in that case, if you have to have some in situ data, or you have to have information which can help you validate these data, in the sense that if in your local region you may not have a lot of in situ data, but you see flooding occurring in certain days or areas, you go back and look at these NASA data and see, did those data sets show flooding in your region? That's indirect validation in your area. But this question is very, very important, because it is not possible to validate globally because there are no in situ data available to do so. And also, if there are in situ data, they all have different qualities. So it is very difficult to come up with one answer for validation. It has to be regionally done. So question 9 and 10, Susanna, you probably can address. Hello, Susanna.
Yes, sure. I was mute. The source of the census data is the National Statistical Offices. That's our primary source. We try to be as close as the original source as possible. In the case of countries that do not have censuses for a certain round, then we use estimates of population. In some cases, stereo censuses, particularly in Europe, they are registered. We use those. But we try to use as much of the official country data as possible. Because they are so diverse, we also use the UN World Population Prospect for the corresponding year, particularly the national data, just to know but if there is a lot of differences, and then we provide both the adjusted and the non-adjusted version of the data set.
I think following questions are also
yes, I was in the middle of answering question 10. So the estimate that are available through the public comparison tool are mostly from the same source of data, in the sense that the raw data are still census data in most of the area. What is different is the methodology that is used to allocate the population to the grid. So in some cases, there are more ancillary data than in others, or the algorithm that they use for the allocation is also different. And that's why we consider that it's very important, the purpose of the use. So what is the data going to be used for? So that you may need better resolution, or you may need to include the population data in your model. In that case, how model or less model the population is could be, the population data is very important. So I think that's part of what the user need to decide, and that's why we have a lot of emphasis on the documentation, so it's possible to know exactly how the data was processed and where they're coming from.
Question 11 is also about mobile app for data management. Is there any app you recommend to build geographic database? Susanna may have the answer for that.
We have the hazard mapper now as a mobile application for both Apple and Android. That's the one that we have so far. And you have to go to build geographic database. Not that I can remember at this point. I'm not sure what I understand to build geographic database. I'm not sure what exactly that means. Most of our data also is possible to have web services, so you can incorporate our data in other services, in other map services. Other than that, I may need to put you in contact with our IT department. They were the one that developed the app and the web services. In terms of question number 12, can we predict the human population by using CDAC hazard mapper tool? Well, in order to predict population, you need to have 2 points in time. That's the classical approach. So the CDAC mapper provides the population at one point in time. I think at this point is the 2015. However, you can go to the original data and look at 2015, 2020, estimate what is the difference, and then simply extrapolate into the future. But it's a very crude way of doing population projections. But
our data is not built in order to work with a long-range projection into the future, let's say to 2030 or 2040. There are other tools that you can use for that, or you can use another approach is that you can use the world population prospects from the UN. There are growth rate for up to 2100, and you can use that with the data that using the CDAC data as the baseline, and you can use that as a very crude way of going into the future. The coverage of the CDAC application is global, but in terms of the hazard mapper, there are some of the data that is only available for the US, I think the flooding part, but the others are global. How should CDAC vulnerability mapper work? Should. Well, if you're using the app or the web base, you basically zoom in an area and you are able to retrieve whatever data is available for that area. You may decide what are the layers that you want to show. Depending on your screen, you may have too much information, and then you can hover on top of that and see information for the different points. Some data is updated daily or every 2 days. Other data has a lower rate of change. So fires and air quality are updated more frequently. The population data is updated as when we have a new version of the population of the world. We are now working in version 5.
So question 15 is about TIPSR, with weather pressure, state impact, and response model intervention. I am not aware of this system. Susanna, if you are, you can shed some light on this.
The weather pressure state. No, I have heard of the system, but I haven't worked with it.
Okay, thank you. Question 16 is about, can we use the flood data for tsunami inundation? So if you use optical data from Moody's or Landsat, they can provide inundation information related to tsunami. Question 17 is, I'm from India working in GIS and risk assessment. What's the minimum resolution which can be used for flood assessment? So that is a good question in the sense that it depends on the watershed you are working with or urban area you are working with. Most remote sensing data we are going to talk about next week, say, are low resolution, 1/10 of a degree to 1/4 of a degree, which is quite coarse. But if you use optical data like MODIS and Landsat, they can be 30 meters to 250 meters. So these are the resolutions available from remote sensing data. Now, combining remote sensing data with hydrologic modeling, then you can get good flood assessment that way. But minimum resolution would depend on the area you're looking at. what we're going to do, an example we'll see next session is for urban flooding, where our resolution of rainfall is not that good, but we use rainfall information average over the urban area and then look at say terrain or impervious surface and slope within the city or urban area to come up with some areas where there may be more flooding than others. So that's all you can do when you have coarse resolution data. So commercial satellites, they provide a few meters resolution, and that seems to work well for flood assessment. Question 18 is how can I get enough data for another country like Morocco? So Susanna already showed how to pick region through Polygon. She had a map where you can pick data anywhere where the data are available. For remote sensing data, also there are tools you can select spatial and temporal what should I say, like spatial and temporal specific information from different remote sensing data sets. We'll see that in next session. Question 19, are there any efforts underway to integrate real-time user reports of flood conditions during the following disaster event from apps such as Waze? Could this be an additional means of verification? There is a Global Disaster Alert and Coordination System, or GDAX. They have a way when a disaster starts, users can provide information. So from news media or from local area, there are also efforts where citizens, scientists report information back. But GDAX is the one center that I know they do systematically. They collect information while the disaster is going on in real time. And I believe that that will happen more and more through apps. People can provide information when disaster is going on. People from that area can start providing information, and that happens all the time. The compilation has to happen somewhere, and I think GDAX is the only center that I know systematically doing that. But I think their information comes more from official channels through different countries and regions, not citizen scientists. So question 20 is, do you have or is there somewhere an example of drought or extreme heat? Actually, next week, we are going to have a guest speaker. She's going to talk about extreme heating cases. And for drought information also, some of the same data sets we're going to talk about can be used. So for flooding, what you use, you can use the same data sets for detecting drought also. So question 21, how much accuracy can show in resilience measurement of an area by the remote sensing system actually? So I think if I'm trying to understand the question, you're asking how with what accuracy remote sensing data can be used for disaster risk assessment or hazard assessment that can lead to resilience. I believe that's the question. And so that accuracy, again, varies with dataset, resolution, different regions. So there is no one answer. And that's why we always recommend that before taking any actions, there has to be a direct validation or inferred validation, that you look at your region, look at the hazard or disaster that you are concerned with, and to build resilience using remote sensing data, try some of these data and see how it works in some cases. And that's why sometimes past data are very useful. You can go back and look at past hazard in your area and see damage occurred or what the impact was on ground from in situ data, and then try and relate remote sensing data to what happened in the past. And that gives you some idea how accurate remote sensing information was that you can use for building resilience.
Okay, I think question 22 for me. Do I understand correctly that most of the population data set are basically estimation average? No, they are not. They are estimate, yes, because the data is matched to a target year, and the census data could be from 1 year before or after. So they are adjustments. They are not averages. We are not trying not to do that. What they are is a transformation of data that comes in a certain system, usually their vector system, into a grid, and that requires transformation. So it's not an average, it's a transformation of the data. There are countries that have very good census data, and the data is also released at a very high resolution. Countries like Brazil, United States, some of the European countries, not all, South Africa, some countries in South Asia too. So they have very high resolution down to the census block or the chassis block in a city. So depending of the country, depending of the data source, you can have higher or lower resolution. DHS could be useful in some countries where you do not have up-to-date census information, but DHS is a survey, which means that you need to factor in the sample, what is the framework, how is the actual coverage. The census, with all the problems, has the advantage of having the national coverage. Of course, that depends on the census of the country, but that's the difference. But that's in terms of the greater population of the world. There are other providers that use other input data in order to allocate the population. So again, it's important to read the documentation to be very well aware how the data set was built according to what are the inputs. And all the providers are very adamant in terms of providing the sources, exactly where the data is coming from and how it was transformed. Question 23, yes, you can download the basic demographic characteristics from the CDAC website. Question 24, the data set, depending on the data set, the population of the world is updated when a new round of censuses come into place. At this point, we are working toward the version 5, and that version is going to include the data from the 2020 round of censuses, so it's just starting the process. Other data sets are updated when new data comes available. For example, the G-roads now, the idea is to try to transform from a very static data set to a more dynamic data set, including OpenStreetMap, but that depends on the data set.
So question 25, and there's also another one I saw down about earthquake. So could you please explain how we relate the surface stress conditions data, uh, alignment change, behavior with the multi-factors data for landslide risk analysis in advance? So there are tools, or there are models which use remote sensing data to have advance notice about landslide risk. Actually, next year, ARSET is planning to have second part of this disaster risk assessment webinar, in which focus will be on landslides, earthquakes, and volcanoes. So at that time, we will be presenting data sets and models and tools that can help in detecting or assessing risk of landslide, earthquakes, etc., etc.
Question 26, are there data set? No, the data set is global. There could be areas within the country that do not have data, but that's also, there is a layer, a grid that describes what is the content of each of the cells, including when the data is missing or what the data, or actually there are no people living there. So that's one of the data quality grids.
Question 7, is there data on loss to agriculture due to disasters? So Landsat data and MODIS data, they have been used to look at post-disaster land surface conditions. And so if their vegetation is destroyed, then you can see that in the images. And so it may not tell you exactly that agriculture, if you know that this is the agricultural area, then the image change after disaster can show you how much the damage was. Actually, there is a very nice example about Hurricane Maria. I think that on one of the Caribbean islands, all the trees had fallen, and you can see that in satellite before and after Landsat image that shows clear difference in land cover. Also, as noted here, ARSET will have a SAR land cover webinar focusing on agriculture and flooding, which will be later this month. And that will have additional information about how one can look at land cover after disaster. Okay, question 28. Perhaps, Susanna, you can talk about using Earth observation.
Oh, yeah, that's a magnificent question. And actually, that's one of the questions in the field. Let's say that in our field of study, how you actually use Earth observation to track demographic changes. And I think that depends on what demographic changes you are talking about. A number of the grids that are available through PopGrid and even through CPW, all of those basically can track the population distribution. So that's the first thing that you can see. You can look at how distribution has changed over time. In some cases with very high resolution, in others with not so much, but you can look at that. That's one of the population characteristics that can be done. Are more difficult, and you need to make a lot of assumptions in terms of those. Another one that is being used now that is the nighttime light. I mean, it has been used for some time, is using nighttime lights to track density, and through that track changes in the urban areas per se, or even the expansion of settlements over time. So those are the ones that could be derived more or less directly from Earth observations. There are some work linking these characteristics through other changes, like changes in socioeconomic characteristics, but you need some transformation of the data for that. But this is a great question, because that's exactly where the the research is happening now. What exactly you can derive from that?
Also, that there is a data set based on Lancet, which provides information about built-up area, human built-up area in surfaces. That can also help in indirectly telling where there is demographic changes occurring.
Yes, and there's at least 2 groups or 2 papers that I know that are using nighttime lights and Landsat for residential and ambient, and day population, just to see they are different in that. So there is several efforts going into this direction.
Question 29, is there any possible solution that can be provided for assessing earthquake risk site for an area immediately by remote sensing techniques? So now that SAR data are available, earthquake monitoring has been done, and I'm not an expert in SAR or earthquake, but if you attend the SAR webinar, and there are also past ARSET webinars related to earthquake using SAR, you might find the answer. Question 30 is about how to estimate the economic value of the assets under risk. Susanna, do you have, or Sean, do you have any specific answer for that? I know that there are economic models, and these models use information about the asset, how old it is, what is the, how was it constructed, or what is the underlying surface condition. Different parameters are used to assess strength and economic value associated with some asset, but I don't know about specifics.
There are some global data set about the economic value of the asset, but they are not up to date. There is one that is they have at least 10 years old or more. But you have the data coming from, for example, some of the insurance companies that have preparing this data. There's very good data for the United States, but that's difficult to assess. That's one of the difficult. But there is a standard about how to provide that data. It's just that the resolution is not always as high as you would like, and depends on how you value the assets. Exactly what Amita was saying. It depends if you are looking at different structural damage and you are looking at other kind of economic impacts, like labor market or work days. So about question 31, yes, we have other data sets that are related to global population. You can explore those in the CDAC website. In the topic, there is a population topics, or in collection you have the population collection, and then you also have another collection under population dynamics, and you have several data sets that you can explore.
Question 32 is, my office is ground satellite receiver for NOAA 18 and 19. How to use that data for DRA? I think NOAA 18 and 19 are operational weather satellites. They have sensors like AVHRR, HERS, and EMSU. So there are products derived from these sensors. I'm not familiar with all the details, but I think they can be used for monitoring, say, land cover, flooding. You can have precipitation from that. You can have temperature from that. So extreme heat can be addressed from HERS MSU data, and so you can provide precipitation information also, I believe. AVHR has a long-term coverage. It has lower resolution than MODIS, I believe, but has similar optical bands. So you can look at inundation or flooding using that. These are my approximate answers because I don't work with NO 18 and 19, but this, based on what I know, I'm so any sensors or data sets which have long-term coverage in time, and it's available in near real time, they can be very useful for disaster risk assessment because you can look at past hazards, learn from past experiences, and then apply in real time.
So question 33, what kind of GIS software one should use to download CEDAC greater population data products? The data is available as a TIFF file. Can you hear me?
Yes, yes, yes.
Okay, I shall have like a warning. So you can, it's available as a TIFF file. There's other products, depending of the product of the global coverage at how big the data set is, could be other file formats. You can use ArcGIS, you can use QGIS. Both of them can be used.
Sean, you perhaps want to address question 34?
Is there any data set to include?
Yeah, sure. So the question is there any database that includes results of national agricultural censuses? For example, land tenure, extension of different crops, etc. So yes, there are. For the United States Department of Agriculture has a branch called the National Agricultural Statistics Service, or NASS, and every year they conduct hundreds of surveys and prepare reports covering virtually every aspect of U.S. agriculture. Again, this is specific to U.S. agriculture, but there are examples that they provide within their database, which are freely available, are production and supplies of food and fiber, prices paid and received by farmers, farm labor and wages, farm finances, et cetera, and I'm providing the link on this document so you can go and explore for yourself. And then outside of the United States Department of Agriculture also has the Foreign Agricultural Service, which has databases as well for agricultural censuses outside of the United States.
So if there are no more questions, we want to thank you all for attending today's session. And we will have the next session on Thursday at the same time. That will focus on actually working with data, demonstration of how to use data using some of the open source tools to aid disaster risk assessment. We want to thank Dr. Susana Adamo for her time and her help with the CEDAC presentation and answering question and answers. Thank you, Susanna. Also, we want to thank the ARSET team. Sean McCartney, my colleague, helped in preparing some of the information. We have Elizabeth Hook. She has edited all our presentations and she's helping with the question and answer as you see here. Brock Levins and Selwyn Hudson-Odoi, they both are responsible for organizing and setting up this webinar and helping in various ways. So we want to thank the entire team and thank you all for attending today's session, and we will see you on Thursday. Thank you.